My background's paediatric biochemistry, and I'm originally from the Children's Hospital. And we've always been interested in microsampling because the smaller the body size, the less sample you can take. So it's something that's inherent in my background. I've moved 7 years ago to RMIT, and I've actually continued along those lines of looking at microsampling. When I was asked to do this presentation, and I'd like to actually just digress now and thank Susie for inviting me here. Thank you very much. And it's been wonderful, and the hospitality has, thank you. I thought about the bioanalytical techniques, and I really thought I could have gone down the point of care pathway as well in talking about analysis, and the mass spectrometry pathway are the two main changes. And I think mass spectrometry has really become our game changer in more recent years, and the way we're actually doing things. And there's a lot of advantages with microsampling, and we've already seen those with the Papua New Guinea things just before. And we can now move outside of our box and really change what we're doing, because we do have some of the analytical tools available to us now. And I think these are going to actually move forward into the future. So my presentation, and I'll just declare I have no conflict of interests that I know of in relation to this, but my knowledge comes, I think, from all collaborations and committees, so I really do need to acknowledge all of these different organisations who you mightn't necessarily know, because I'm from a slightly different world, I suppose. I'm going to go through a little bit of the history to see where we've actually come from with mass spec, and then I'd like to talk about specificity as I see it, then sensitivity, and then look very briefly at the matrices, and then the near future and some of the things that are about to happen or are happening. So GC was where we probably started in our mass spec journey before we actually even got to the mass spec. So this is a bit of a history diagram. It is related to steroids, but it's got drug doping in with steroids in there. And really what I want to show you is we're getting close to 75 years or so where we're actually looking at chromatography-based techniques and separation sciences to improve our analysis. We've started from GC back here with flame ionisation detection, urine as our primary matrix, and 25 mils maybe of sample that we've needed. And we've moved a long way in the 70s, and in the clinical space, GCMS came in the 80s, to my knowledge in Australia anyway, and SPE was introduced, solid phase extraction. Up here we were doing liquid extraction and really just doing very simple things like adjusting pH and things like that, so maybe adding hydrochloric acid. Down here we've got 10 millilitres of urine now in this space, and as we've moved down, we've really hit this change, this game changer, and that's LCMS. And that game changer really revolutionised newborn screening, which is our traditional dried blood spot group. And we know that from the 1960s when Robert Guthrie actually introduced it. But up until this point, I really think I did a little bit with dried blood spots outside of newborn screening, but really it stayed within newborn screening until we've had this opportunity to open up with the mass specs, with the LCMS. And it's now, I'll show you some data where it's actually just expanded, and it's actually in your world that it has expanded, but I'll show you that later. And the other thing that I think has changed more recently is supported liquid extraction as part of our sample cleanup. So all of these things are now making us being able to do things better and on smaller volumes. So it's not all rosy. These are the wonderful people who got the Nobel Prize for the LCMS. between them. We did have a period in the mid-2000s. We thought everything was wonderful when LCMS was first introduced, and then we realised we actually had a lot more challenges than what we thought of. And probably one of the most notable examples of where LCMS has fallen over is with the recall of, I think, thousands of vitamin D results from Quest in the mid-2000s. And that really made us a bit more suspicious and uncomfortable, but I think we've moved on from that, and we've actually now understand and are really progressing our LCMS systems in terms of being able to have a really good qualitative and quantitative results that are fit for purpose. So I think there's a lot of excitement, and I'm really excited about this area. The other bit that I want to tell you that people don't really think about, we haven't spoken about metabolomics this morning, and that kind of surprised me. We've been looking at discrete quantitative analysis so far, but I think the metabolomics space is really, really exciting, and we consider that a really new space. But I hate to tell you, it's been going on since the GC days in steroids and also in drugs. The main difference, I think, besides that we're now adding mass spec into it, we've got all this data that we're trying to analyse. And it's actually the analytical tools and statistical analysis that becomes far more interesting. So I've got a very standard profile, metabolomic profile of a urine here, of a male urine, but you can take multiples of these profiles and put them together, and so I've got 3 male and 3 female urines here, and you can actually tease out the differences in the metabolome by just doing statistical analysis if they're all in the same run and it's all on a scan mode. So I think this is very exciting, and it is this statistical analysis that has the huge expanse along with the mass spec components there. Now, to make sure I stay on track with some drugs, I've borrowed from from Laurelie Langman's group at the Mayo Clinic, who wrote this nice article on mass spec in toxicology. And this was published in December 2016, so I think is relatively fresh. In the traditional steps for toxicology anyway, we had very simple processes. And our processes have become a little bit more complicated with mass spectrometry. And we actually need to consider each of these processes to make sure that they're optimised. In addition to this, we've got the complication of different types of samples. And I'll just say this article is freely available online, so you could download it if that was of interest to you. I want to talk first about specificity, and specificity in my world and my terminology is different to population studies of false negatives and false positives. I'm talking about making sure we have the right analyte, we understand what we're measuring. And so we might call that the measurand, and mass spectrometry actually makes it very specific with what we are measuring, and that's a huge difference from our immunoassays, which are less specific often. So we actually have a higher order approach, but we still have to be careful because we can have interferences that actually will affect specificity. I'd like to take you on a tour. And with permission of Sam, his photo is in here. So this is a mass spec in my lab, and it's a 2D system. That's the chromatography component and the mass spec here. And we're opening up the box. So let's just have a look what we've actually got. So when we open the box, we've got electrospray ionisation, which is a soft ionisation source. So we have, if we're breaking a Greek plate, we're breaking it something like in 2 pieces. as distinct from a GCMS where we'll be smashing the plate in our process into multiple pieces. So we do this and then our quadrupole here is our first one, and mass spec 1. Then we have a collision cell. The Greek plates here, and the mass spec 2, which is another set of quadrupoles, and then finally a detector. So this is nicely set up, and let's have a look at what the quadrupole does in terms of selectivity. So a quadrupole just means 4 poles. Okay, very simple. From one end you can see the 4 poles here, and this is actually going through the system. Now, as a sample goes through the system, we have multiple analytes in it, and we can choose to only allow one of our drugs to actually enter into the main system. This is a SciEx animation, just by the way. I'm jumping between companies willy-nilly here, taking the best of everything. And then we're doing our collision in here with our black drug and dividing that up into 2. And then we're filtering for quantitation, and we are choosing just the blue. So we become quite specific in our whole process. And this is wonderful. And we used to think, though, that we could just put our sample directly into the system of the mass spec with this process in a dilute and shoot approach. And we now know that this probably isn't enough. But by the time we have this multiple reaction monitoring, we can actually do a diagram where we've got the first quadrupole here and the second one on the y-axis, and we can divide up our compounds because they'll have the very distinct mass to charge ratios. We do, however, need the chromatography component, and the choice of column is really important because we need to actually separate isomers and epimers from what we're actually looking at. And so this has become a very important consideration. And I won't go into that too much more, but it's something we always have to keep in mind. And especially with the drugs, there might be variations that might be the same mass to charge and very close molecules. In terms of specificity, we have a number of mass spec analyzers now in toxicology, and once again this is from Laurelie Langman's article, and I've put it into a table. So they have the quadrupole systems, which probably have the lowest of the resolution, and the ion traps are used, and time of flight, and then sector. With the ion traps, there's often a quadrupole in the first part of it, and the time of flight, there's also often a quadrupole in the first part of it now, is where things are moving. So this is where we're at, and I think this is where we're probably heading down here. And we'll improve our specificity, and we'll also, as we move forward, we'll also improve our sensitivity. So sensitivity, what does that mean? It means how low can we go? And this becomes really important because if we've got a large sample volume, we don't need as much sensitivity. If we've got a smaller sample volume, we need more sensitivity to balance out using that smaller volume. And there's a lot of considerations to achieving good sensitivity is the sample volume itself, the sample cleanup process, and whether we need to derivatise, because derivatisation can improve sensitivity, and scanning versus a single ion monitoring or an MRM mode, multiple reaction monitoring. And I think one that pulls my hair out is ion suppression. And I think that's something that potentially affects dried blood spot analysis. So I have a term, and I won't use my German swearing words, which I use occasionally for this, rubbish in, rubbish out. we need to have very good front end for dried blood spots, and I think that's fundamental. And this is part of the mass spectrometer just having a bit of a clean up, because if it's dirty, or we've put dirty samples in it, and I've seen some really dirty samples go into other mass spectrometers, they're useless. And if we don't know enough about the mass spectrometer and we don't know how clean it is, we don't understand the quality of our results being generated. And so having key operators is, I think, really important, who you can trust to actually look after it, okay? And I think we have a lovely example in the room with Monday. Okay, pulling my hair out, this is not my slide, this is a student's slide. So I run a project every semester. I have 40 students and I divide them up into different projects. This semester I've got 10 of them on mass spectrometry, and they're developing a method. And they're part of the developing a method. It's just a cortisol method. It's nothing too hard. I give them some base reagents and they have to work with it. And there's a point in time where they come up with, I can't get it to work. And it's all about these little darlings, phospholipids, just interfering. And it's a particular problem with blood matrices. So phospholipids, think about membranes, and there are two main culprits, which are 104 and 184. Just remember those numbers. I won't explain them too much, and I find the 104 tends to be my main interference in higher amounts, but both species are present. And this is an example of where monitoring phospholipids, and this is the 184 phospholipid, and this is what we're trying to find here, and a poor little testosterone under here, and we've got so much phospholipids that everything is suppressed. And what I think a really good example of that is when you try and quantitate and you do serial injections of different volumes, and you actually see your curve go in the opposite direction, because the more phospholipids you put in, you get a big change. Ultimately, this causes us sensitivity problems. If we can get rid of the phospholipids, we actually will improve our sensitivity, often significantly. So let's have a look at matrices now. And I do know Brett is coming in to talk, so I promise I'm not going to steal his thunder on this. But we've got a number of different matrices, and this is a slide from Thermo Fisher. Now I've changed companies again. And urine, hair testing, blood, sweat, and saliva and oral fluid. And I think the saliva is quite a common one. Sweat's becoming quite interesting in the metabolomics space at the moment. And hair testing is actually being investigated in the forensic labs in Melbourne as a study. They've all looked at dried saliva spots. So rather than wet saliva, the forensics lab in Melbourne has done that recently as well, last year. And I read something this morning about tears, and I thought, oh no, how would you collect tears? But tears was something that you could actually also use. Getting too hard. I'm going to concentrate on blood here. And the dried matrix, and there's a lot of advantages of the dried matrix, and this is our publication from last year, and led by my most senior PhD student, Rosita, and looking at dried blood spots outside of newborn screening applications. And most of them are related to drug studies in some form, whether it's toxicological or pharmacological. We know all of this, so I don't need to repeat that, but basically these dried approach can be used, I think, quite easily for blood, urine and saliva. And certainly urine's been used for many years in the metabolic screening processes, where it might be from a filter paper. And we actually, as part of some work that I've been doing with Sri Lanka and Algeria, don't ask, I actually developed a protocol for the collection of dried blood spots, and we adapted it into a picture format into this publication. This is a review article, and the collection is so important that we've already heard. In that review article at the time that we submitted it, which I think was September last year, there were 121 different applications outside of newborn screening for dried blood spots by mass spectrometry. And most of those were in the LCMS space, and most of those were on triple quads. So it's certainly here. When we're looking at the dried blood spot process, we've got the collection, which we've heard about and seen how difficult that is. How we extract is also going to vary depending on our analyte, and our analyte stability also, and understanding that. But there's some really, I think this is a really nice process now where we're actually got this SLE that's moving in, supported liquid extraction, to help give a better cleanup and removing phospholipids in some phospholipid plates. And finally the analysis, which has looking at the literature, does run across GCMS, LCMS, and also with direct MS applications. And I should say I use MS liberally here. I could mean a single quad or triple quad, okay, in my language. So another thing that will actually be really important for sensitivity is making a decision about whether you want to measure the compound itself as the compound or whether you want to derivatise it. And this is an example. Apologies, it's vitamin D. It's not necessarily a drug, but we do administer it, so we can call it a drug at times. And we have vitamin D. We could do a liquid extraction of it. We would like to separate our epimer from vitamin D, so we need the right column. But on a dried blood spot, we might not get the actual sensitivity that we need. So this is a serum sample, and then this is a dried blood spot sample with a much lower axis here. And so what our limit of detection will be really high. And where did that go? So over there. And so assay sensitivity by this approach on a dried blood spot, a 3 millimetre punch might be 150 nanomoles per litre. Well, I don't think that helps given our limit, our cutoff is 50. So it doesn't work. So a lot of people in this space, whether it's vitamin D or anything, are looking at derivatization, but derivatization has some of its own problems. Do you get 100% derivatization? Well, you can actually check that if you monitor it by mass spec. Are you going to be able to achieve the same separation? And in the vitamin D space, it's really hard to achieve the separation from the epimer once you derivatize with the common PTAD, derivatization reagent. But there's new derivatization reagents coming out on the market and that actually are allowing for better separation because of changes in the configuration. And once again, the SLE, I think, is really the way forward for ensuring we have a good clean sample to get our sensitivity. And now we have, finally, a nice blood spot when we've done this derivative that is actually matching our sensitivity of serum. And our signal to noise at 6 here gave a 0.5 nanomole per litre. So we've gone from 150 to 0.5 in this just by using the change in process. I'll just spend 1 minute on here, and I just want to point out, because I think this is important and it's been brought about before, when we have a very low hematocrit, we tend to have more diffusion of the blood as well. Besides the different ratio of plasma to blood cells, we have a broad band. So what we actually punch and we say is a certain volume, if we're trying to convert it to plasma, will be quite different to someone who's like a neonate who maybe have a higher hematocrit. And this is, I think, the real confounder. Okay. I think this is our next problem, and I'm on my way to finishing now. We've got a bit of a mess with our mass specs. We do these hybrid approaches, so I don't think we can easily totally transfer one method to another. We've got different lengths of tubing, if I go down to something really simple. So we're going to have differences in retention time and slight changes in gradients and so forth. And I think we really need to work on this approach and how we can do this. Now, there have been companies that have been working on this, and Thermo, I saw in June in Athens, this instrument, and I'll just show you what they're doing. I don't think it's necessarily for dried blood spots yet, and it is a prototype. So it is now, looks like an immunoassay analyzer. It's a mass spectrometer, and we just load the samples in the same way. And we look at the aliquots. It will automatically aliquot internal standards. Everything is closed in. We will incorporate the mobile phases, which are all on board and all from the same company. It will do an SPE cleanup, and it has its own specific column for the separation. And the mass spec will be ESI and APCI, as is what they're saying at the moment, and it's a triple quad. And then we have a validation screen. So we're becoming far more black boxed, but I don't think that's the space necessarily for this area, but it's one of the directions of the future. And in my last approach, I think we have, we're going to actually see, we're going to continue to have lab developed tests because they're needed, but this, and we're going to have a kit user system, but this fully automated lab solutions, I think, is where we are heading. And in addition, bedside or point of care testing with mass spectrometers is the next step. So I think there's going to be a space for all four approaches as we move forward. And from what I can see, I think we'll end up moving probably away from triple quads and towards QTOFs, because we'll have a broader range of analytes as well. And we do have new standardisation challenges with dried blood spots. And on that note, thank you very much.